the large-scale packed bioreactor for remediation of groundwater contaminated with MTB and TBA. Methyl butyl ether, or MTB, is a synthetic car fuel additive which is very soluble and mobile in groundwater, and therefore it can pose a substantial risk for underground drinking water reserves. TBA is a stable byproduct of MTB biodegradation under anaerobic conditions, and it can be often found in MTB contamination plumes. Today, we have only a few studies which have applied MTB and TBA degrading bacterial cultures for bioremediation of MTB, but have not yet evolved full-scale applications. In the last 10 years, a number of MTB degrading pure strains and mixed microbial cultures have been isolated and use MTB as the only source of carbon and energy. At Vito, they have isolated the mixed microbial consortium, which is designated as M consortium, and is enriched from an MTB contaminated soil. This consortium contains mainly beta protobacteria and has the ability to use MTB, TBA, and BetaX as the only carbon and energy source. It also contains more than one bacteria, which contribute to MTB and TBA degradation in the mixed culture. Finally, the M consortium has been successfully used for biodocumentation of MTB contaminated groundwater laboratory scale and pilot scale bioreactor experiments at Vito. Here is the Vito large-scale packed bed, which is an upflow bioreactor of 7 liters total volume, includes a recirculation loop, and 4 sampling points, one sampling the influent, one sampling the effluent, and 2 internal points. Also, it is filled with expanded clay particles as carrier material for the immobilization of the M consortium. This bioreactor has been tested, and it has been found efficient for the ex situ bioremediation of MTB contaminated groundwater below the Flemish discharge limit, which is 0.1 milligrams per liter. Here is a set of raw data from the bioreactor experiments conducted at Vito. Initially, the bioreactor has been inoculated with a very small amount of inoculum, and at the batch period, which lasts for 14 days, this M consortium has been attached to the carrier material. After this period, we have a continuous flow function of the bioreactor, where initially we have a very high hydraulic residence time, which means a very low volumetric flow rate. Gradually, this HRT is decreasing, as you can see, and 1.6 hours is the minimum HRT possible for the system. Because reducing HRT to a lower value, which is 0.6 hours, you can see that we have a peak in the effluent MTB concentration, which means that the system cannot biodegrade all the MTB amount inserted into it. This is also shown by the curve below, the dissolved oxygen curve, where you can see that also dissolved oxygen has not been utilized by the M consortium. We wanted to express the system's behavior into equations, and by mathematical modeling we could determine all MTB and TBA degradation process kinetic parameters. We could predict the biomass and contaminants concentration profiles along the column bioreactor with respect to time, calculate operating parameters such as the minimum hydraulic residence time and the maximum MTB removal rate, and we could predict also the process performance as a result of the variations of the process conditions, temperature, pH, dissolved oxygen, and nutrients. And we could also predict cell washout and bioreactor overloading phenomena and design best operational strategies such as viable HRT implementation. Up to this point, the modeling activity aims to the simulation of the general bioreactor behavior and its species dynamics, the calculation of the minimum HRT required in order for the effluent MTB concentration to be within the specs, and the simulation of the bioreactor's behavior under viable HRT. We have used MATLAB as software for the algorithm development, and we have considered three-state variables, MTB, TBA, and biomass. We have discretized our bioreactor column in 4 compartments with an effluent recirculation and a constant influent concentration. And for biomass, we have considered that it is transferred from one compartment to the next when biomass concentration reaches a maximum value corresponding to full loading. For the biochemical processes, we have considered monotype biomass growth for biomass, and MTB and TBA use as carbon source for maintenance energy and biomass synthesis. However, we took not into account transfer resistances mass transfer resistances in nutrient transfer and oxygen eliminations. Here are the model equations we have used. We have 3 mass balances for each one of the compartments. We have a mass balance for MTB, a mass balance for TBA, and a mass balance for biomass. Both MTB and TBA mass balances include an input term, an output term, a term of consumption for biomass growth, a term of consumption for biomass maintenance energy, and a term of TBA production from MTB. For biomass, we have considered that biomass grows both on MTB and TBA. We have simulated the experimental runs using the employed HRT, and we have predicted biomass, MTB, and TBA in each of the 4 compartments under batch and continuous operation. And we will also show you a simple rule for variable HRT implementation, where HRT is adjusted by this rule whenever the effluent concentration is well below the required limit. Here is the simulation of the bioreactor dynamics for a constant HRT implementation. The HRT we have implement is very high. It's very high, 18.24 hours, which means we have a very low volumetric flow rate. With this low flow rate, the effluent of the MTB in the effluent remains at all times below the discharge limit. It's the red solid line. You can see. But we have an initial period where MTB has a peak in each of the 4 compartments. This is because we have at this time very low biomass, because time of function. And biomass grows primarily in the first compartment, which is sufficient to degrade most of the incoming MTB and TBA produced. This is the black solid line on the first compartment. We have a linear biomass growth, and this is because biomass growth is proportional to the total MTB amount inserted into the system. And so for the given biomass concentrations, it is obvious that after 5 days, we could reduce the HRT, which means we could increase the volumetric flow rate of the system. Here you can see the effect of the HRT reduction or the volumetric flow rate increase. As the volumetric flow rate increases, you can see that we have a much greater peak in the MTBE concentration in all 4 compartments, which means that the system cannot initially, because of low biomass, degrade all the MTBE inserted into the system. Also, here in the 3rd plot, you can see the way we run the biomass excess in the bioreactor, which means that after we reach a maximum in the biomass, in the first compartment, biomass goes to the next compartment, which is the 2nd here. Here is the simulation of the bioreactor dynamics with the variable HRT implementation, which was also the case in the experimental runs. Initially, we have an MTB concentration increasing in all 4 compartments due again to the low biomass. After when we decrease HRT gradually in a stepwise fashion, where after every HRT reduction follows an increase in the MTB concentration in all 4 compartments. But we have at very high HRTs, which are 0.6 and 0.3, a significant increase compared to the others. This is because at very low HRTs, as you can see here, a small decrease in the HRT results in a very big increase in the volumetric flow rate. And at the plot below, you can see the biomass of the bioreactor, and you can see that the bioreactor is up to this point overloaded and full loaded. And effluent MTB concentration, you can see that it's for most of the time below the discharge limit. Is again the red solid line. So based on the simulations, the packed-bed bioreactor will reach a maximum biomass concentration after a certain period of time, and then it will remain constant, and we have then free cells in the outlet. So the HRT can be systematically reduced to a minimum value that corresponds to the maximum biomass concentration, and whenever this is done, we should wait for a period to see whether the system reaches a steady state, which means whether the effluent concentration will be below the limit. So it is better to reduce HRT gradually rather than in big steps. And in real-life operation, the bioreactor's performance is much more complicated. For example, we can have blacking due to excessive biomass increase, and thus channeling flow resulting in nutrient limitations in certain areas. And here you can see an idea, a simple rule we have to decrease the HRT for the system. When we are at steady state, all the incoming MTB into the system is biodegraded and converted to additional biomass. So we have unexploited biomass for this HRT, which means that the system is capable to degrade much more MTB. As biomass increases, the MTB effluent concentration is decreasing beyond the limit, and hence we could increase the volumetric flow rate and stay within the limit. It can be shown that the increase in the volumetric flow rate can be computed from this equation, where you can see that we need biomass measurements. And since we want to avoid these measurements, we can only monitor the MTB effluent concentration, and whenever it drops below 20%, we could increase the volumetric flow rate by a specified small amount. So as conclusions, during the operation of the packed bed, there is a continuous biomass build-up, and when biomass increases substantially, we can lower hydraulic residence time, meaning increasing the inlet flow rate. During the first 130 days, we do not have any cells in the effluent, and at this point, the bioreactor is essentially at full capacity, and we cannot reduce HRT further. Thank you very much.